In this short video presentation, I describe the process of dissociative ionization of multi-electron diatomic molecules in a phenomenological manner. In the present context, we are mainly interested in dissociative ionization of a molecule following the interaction with a short laser pulse of attosecond or femtosecond duration, or a combination of such pulses in a pump-probe scenario, where, for example, the XUV attosecond pulse can be considered to be a pump pulse and the infrared femtosecond pulse a probe pulse. In such a pump-probe scenario, the delay between the two pulses will be important, and the experimental result or the outcome of theory will depend on this delay. Measurements performed in this manner constitute the basis of attosecond XUV IR spectroscopy, and this is one of the key approaches for characterizing the attosecond and femtosecond electronic processes and nuclear dynamics occurring in molecules. And this now brings me back to the dissociative ionization process triggered by laser pulses. In dissociative ionization, we have dissociation of the molecule, meaning that the nuclei fly apart, and we have at the same time electrons being kicked out into the continuum and propagating away with positive energy. For the rest of this presentation, to make the discussion specific and as simple as possible, I will consider as an illustrative example the simplest possible molecule, namely H2. In H2, we have these channels in the dissociative ionization process. One channel could be that the molecule ionizes and leaves the cation behind, and maybe the cation will dissociate into a proton and hydrogen atom. Alternatively, we can have the complete breakup channel where as an outcome we get 2 protons and 2 electrons. Experimentally, we could consider a setup as shown in this view graph, where a molecular beam is intersecting a laser beam, and in this case the charged electrons and the charged nuclei are measured. On the screen over here, we imagine that we are capable of measuring the total kinetic energy in those 2 protons, and this gives rise to what we call the kinetic energy release spectrum. A typical kinetic energy release spectrum is shown in this view graph, where we have the kinetic energy release in electron volt on the x-axis, and we have the signal in arbitrary units on the y-axis. And what we see is a spectrum which is characterized by a low energy part, high energy part, and an intermediate energy part with some structures. In general, with such a spectrum at hand, it is the aim of theory and experiment to understand the structures in this spectrum in detail and to decode the information about the ultrafast dynamics. Of course, we cannot go into much detail here, but we will point out that often much useful physical insight into the dynamics of dissociative ionization can be obtained by considering the most important Born-Oppenheimer curves. That is, we consider the electronic problem for fixed internuclear separation and solve for the electronic energy. And this we now do for a range of relevant internuclear distances. A sketch of the most important curves when H2 is exposed to near-infrared 800 nanometer light of femtosecond duration looks like this, where I sketched curves in the neutral, in the cation, and in the dication. And what you see here is a blue curve for the neutral system, 2 green curves for the cationic system, the one is sigma d and the 2p sigma u state, and an orange curve giving the Coulomb repulsion 1 over capital R between the two protons. Now, initially the system is in the neutral system, and when we turn on the laser, it will couple to the ionic system as sketched here by this red arrow. In the ionic system, dynamics during the laser pulse will happen, and couplings will occur between these states involved as sketched here by the black arrows. In this system, the nuclei may now dissociate or perhaps ionize a second time, which would bring the system to the ionic curve. If the nuclei are at a relatively large distance when a second ionization happens, not much energy is stored in this 1/R potential, and such an event will lead to a signal in the kinetic energy release spectrum at a relatively low energy. Conversely, if this second ionization happens at a smaller internuclear distance, there's more energy stored in the 1/R cooling potential, and such an event will lead to a high energy, will lead to a signal at higher energy in the KER spectrum. In this simple picture, it's already clear that the shape of the kinetic energy spectrum carries significant information about the dynamics in the dissociative ionization process. And it's also plausible from this picture that more information about this process can be extracted by considering setups where pump and probe laser beams are used. In that case, the shape of the KER will also depend on the relative time delay. This finishes the discussion on dissociative ionization.